All right, students, this is our final video for topic 2.3, work, energy, and power. And just to kind of refresh your memory of the things we've talked about, we spent a lot of time talking about work as being force through a distance measured in joules. Then we talked about how work is related to energy. When we do work on something, we give it energy. We talked about the conservation of energy. And in particular, we spent a lot of time talking about gravitational potential energy and kinetic energy and different kinds of potential energies. Okay, so we're going to pull it all together now, and we're going to introduce time into these concepts. And as I've alluded to before, the rate at which work is done or energy is transferred is referred to power. Okay, so in the case of this this old-fashioned coal-fired train, it's the combustion of coal in the engine. Coal is a fossil fuel. It contains a lot of potential energy, which are from ancient dead plants, and we'll talk more about that later when we talk about energy production. It's the combustion or the burning of coal in that engine that transfers chemical potential energy to kinetic energy in the simplest sense. Okay, the train exerts a force through a distance on the wheels. So work is done on the train by the engine, which indirectly is done by the combustion of coal in the train engine. So here we have a transfer of energy where work is done, and as the train moves, because it had work done to it, it increases its kinetic energy. So then we see lots and lots of examples again of transfer of energy and the intimate relationship between work and energy. Now, the rate at which the train speeds up is really important, and I think that we would all agree that it takes a stronger engine to speed the train up more quickly, correct? And when we say it's a strong engine, we really mean it's more powerful. You could probably say that at the same time. Now, this is one of those times where sort of the common usage of an English phrase or an English word is actually the same in physics as it is everywhere else. We say that when work is being done faster, we have more power. There's a more powerful engine. When work is being done slower, or at a lower rate, it's less power, less powerful, okay? Which leads us to our formal definition of power. And power is simply the rate at which work is done. And remember this term rate. Rate always means something done per unit time. So we have power as work per unit time, P equals W over T. The SI unit is a joule per second, which is called a watt. I need to tell you about another unit that's quite common, and that's horsepower, which comes from the old days of horses pulling buggies. We don't use this in the IV. It's not an SI unit, but a lot of cars nowadays, the engines are still rated by horsepower. You should be aware that 1 horsepower is about 750 watts. And power is a scalar. And really it's an average over a time interval, okay? When you guys get to college, and if you take more advanced physics courses with calculus, you will be dealing with variable rates at which work is done and energy is transferred. We don't really have to worry about that in this course, and we're going to consider this equation to give us average power. Okay. Now, just like the joule was defined by the concept of work, the watt is defined by the concept of power. And 1 watt is exactly 1 joule of work done in 1 second. And I think you can see that 1 watt in terms of SI base units gives you 1 kilogram times a meter squared over a second cubed. So you need to be aware of that, of how joules and watts and SI base units are all related. Okay. Remember we talked about the mule pulling that 50 kg crate. Okay. If the mule applies a force of 150 newtons on that crate, the work done by the crate by the mule is 750 joules, of course. If the mule does this work in 12 seconds, then the power dissipated is 63 watts. So you can see that as time goes down, the power goes up because time is in the denominator of this fraction W over T correctly. Remember, the joule was the SI unit for energy and work, and by doing work on something, we could give it energy. So what this means is that power can now be thought of as the rate of change of energy. So we could say that P equals W over T, which is also delta E over delta T, okay? And I want to make a connection to biology here, and I want to alert you to something called a metabolic process. This refers to a process in the human body which converts chemical energy inside of food into useful energy. Remember we talked about different foods having different calories. That's the amount of chemical energy basically inside of food, and a calorie was just another unit for energy, we don't use calories in the SI system. We use joules, but really it's all the same thing. Okay. Note that running requires a lot more power than sleeping. For a young 70-kilogram male, okay, which is a lot of you boys, I guess, watching this. This would be like a healthy teenager, male teenager. To run 15 kilometers per hour requires about 1,340 joules per second. Sleeping requires about 77. So sleeping is not a completely sedentary activity in terms of the rate at which energy is dissipated. Okay. All right. Example 1. This should look pretty familiar to you guys. The last time we did this, we talked about the work done for the girl to pull the suitcase through the airport. Now I'm asking you to find the power exerted if she does this in 55 seconds. So go ahead and pause the video and try this one. Okay, I got that the power exerted is about 40 watts. It's simply 2170 newtons, which is what we found before. This should actually be joules, of course, because it's work. That's a mistake. Okay, probably caught that in the last video. So 2170 divided by 55, and that gives you about 40 watts of power. Okay? Okay. What's the minimum power required to lift a mass of 50 kg up a vertical distance of 12 meters in 5 seconds? Try this one. Remember that we made the simplifying assumption that when we lifted things up through a distance, that what this means is that instead of accelerating the object, we're applying a force on it upwards equal to its weight. And if we make the simplifying assumption, we have that power is mgh over t. In this case, it's 1200 watts. Okay. Now, you probably noticed that a lot of appliances and electrical devices in your houses have power ratings. So, for example, here's a microwave. I got this fancy microwave. It's a high power microwave, 1200 watts. Well, what does that mean? What that means is that when I plug it into the wall here in the US, where the potential difference between the two plugs is 120 volts, which we'll talk more about later, it means that this microwave is capable of delivering 1200 joules of energy per second to the food to heat it. So I guess that's considered a high-powered microwave. Okay. Now light bulbs have power ratings as well. Okay. This is a 60-watt bulb. Okay. This light bulb is designed to deliver 60 joules of energy per second to a filament, which is that small device inside of a bulb that gets real bright when there's a current passing through it. Okay. All right. It's designed to deliver that amount of energy per second when it's connected to a 120 volt potential difference. And again, we'll talk about that later. This bulb is dimmer than a 75-watt bulb, which is designed to deliver 75 joules of energy per second to the filament. Okay? Okay, so I want to talk again about the pendulum, okay, and what we've learned about gravitational potential energy and kinetic energy, okay? This is a really sweet GIF because it shows the energy curves for kinetic potential and total mechanical energy for a pendulum as it moves back and forth, okay? I just want to remind you guys that the work done by the pendulum on the pendulum, is done by gravity to bring it from the top to the bottom. And this is the change in potential energy between the top and bottom of its swing, which is determined by the vertical height h, which is between the x-axis and this white line showing the total mechanical energy up here. Okay. Now, since the change in potential energy equals the change in kinetic energy by the conservation of energy, we could find the swing of the pendulum at the bottom of its swing. We could find the speed of the pendulum at the bottom of its swing, which we've done many times before. The work done is equal to the change in energy. So if we know the time taken for gravity to move the mass from the top to the bottom, we could actually figure out the power of gravity, in a sense, on the mass. The time taken to get from here down to the bottom is actually 1/4 of a period, because a half of a period is one swing, and a full period is two swings, one across and one back to where it started, okay? So therefore, the power dissipated by gravity and moving the mass from the top to the bottom, we can think about it two ways. We can think about it in terms of potential energy, that's 4mg delta h over the period, or we can think about it in terms of kinetic, which is 2mv squared over t, and the v in this case would be the speed of the mass at the bottom of its swing. You don't really need to know all this for the IB. This is just kind of an interesting sort of thought experiment that this would be easy for us to verify in the lab, and maybe we'll do that. But you should be able to kind of come up with alternate expressions for things like power, work, and energy using some of the other concepts in physics that we've already studied, like the period of a pendulum. Okay, so another way to think about power, okay, power, work per unit time, work is force through a distance, but that's really force times distance over time. I'm just drawing my parentheses around my distance over time. And you know that distance over time is speed, or if it's displacement over time, it's velocity. So in fact, here's another equation for power. It's F dot V, which is FV cosine theta, okay, where theta is the angle between between the force vector and the velocity vector. In your data booklet, the only equation you're given for power is this one. You are not given that power is work per unit time in your data booklet explicitly, so you need to be able to work with this equation. In this case, as before, it's the average power, and if that's the case, it's the average speed that you're talking about here, okay? Okay, let's try this one. Pause the video and try this one, and then start it again to look at my solution. Okay, so I have a car starting from rest, accelerating in the positive x direction. I know its mass, its acceleration, and the time. Determine the average power, okay? Pretty straightforward. So P equals FV, which is really MAV. In this case, we need the average speed, and I guess you'd need to really make a Suvat table and use one of the equations of motion. I got that the average speed is 11.5 meters per second, and then all you do is you put this 11.5 meters per second into this equation, and I got 5.82 times 10 to the 4th watts. Okay, here's another one. Here's a past paper question. You may have seen this question before or something like it. This is probably a part of that question you haven't solved before. Go ahead and pause the video and try this one. Okay, so the minimum power output of the car engine needed to move the car from the bottom to the top of the incline. Remember what the car is doing work against. The car is doing work against two things in this case, against gravity in the vertical, but also against friction. This is not a frictionless problem, and friction tends to pull the car down the plane. So we have two different agents that we have to do work against when we're dealing with the power output of the car engine. So we have to account for both of them, okay? First thing I'm going to do is I'm going to figure out the time taken to get to the top. It's very easy. I got that it's 300 seconds because I'm given the speed of the car, okay? And I'm going to break it into two parts, this problem. I'm going to think about the work done against gravity to get to the top. I get 3.6 times 10 to the 6th. The work done against friction, I get a little bit less than that, okay? So the total work done against gravity and friction, I get 6 times 10 to the 6 joules, which is the sum of these two, okay? And so the power would be that amount of work over the time, which I figured out before was 300 seconds, and I get about 20 kilowatts, okay? So that's the minimum power needed to move the car from the top to the bottom of the incline. We're not talking about the power needed to move at a certain speed or whatever. That's the minimum power output. Well, I guess that is to maintain the speed, but we're not talking about increasing the speed or anything else, okay? Okay, I want to talk to you about efficiency, a very important concept that will come up again and again and again in this class, especially when we talk about power generation and power plants and electricity and all those kinds of things, okay? In every energy transfer, some energy is wasted or dissipated. We often neglect that, but that's actually really important. And usually energy is wasted or dissipated as heat. That's why things heat up through friction, okay? The less energy that's wasted in a process, we say that its efficiency is higher. It's a very efficient process. The more energy wasted, the lower the efficiency. And the efficiency of any process, whether we're dealing with mechanical, kinetic, potential, thermal, chemical, whatever, the efficiency of any process, there's the ratio of useful amount out to the total amount in. Now, in the case of energy and work, that's useful work out over the total work in. Your data booklet will tell you that it's also useful power out over total power in, which makes sense because power is work over time, and the time just cancels out in this second equation, okay? Very, very simple concept. It's easy to make a mistake because you have to keep track of your total amount in and your total amount out, which is not always obvious, okay? So in this example, let me walk you through this. The nuclear power station produces 10 gigawatts of power. The power generated by the reactions in the core of the reactor is 25 gigawatts. Determine the efficiency of the power station. Well, clearly if it's producing in the core 25 gigawatts, but it's only producing 10 gigawatts of power that it sends out, that means it's losing 15 gigawatts of power, okay? But we don't even really have to consider that. All we have to do is say, okay, well, the efficiency is 10 gigawatts over 25 gigawatts, okay? In this case, 25 is the total work in, and that's a 40% efficiency, which is not that great. Okay, try this one, example 6 on your own. Okay, so I have a 10 kg box being pulled along the floor by 2 meters. What's the efficiency of the agent or the thing pulling the box if the frictional force is 20 newtons? Okay, well, the work done on the box by the thing pulling it, I got 100 joules. The work done on the box by friction would be 40 joules, okay, because remember this is 20 over the course of 2 meters. The useful work done on the box to move it would then be 60 joules. Therefore, the ratio of the useful work out to the total work in is 60 over 100, which is 60%. Okay. Another way to think about it in this case is the following: the net force acting on the box is positive 30 newtons to the right. Okay, and work is really the product of the sum of all forces times the distance. So that would be 30 times 20, which is 60 joules, which maybe is a more common sense way to think about it. Okay, here's another example of a bus going up a hill. Why don't you go ahead and try this one? I think this is our last example. Okay, good one, past paper question. Okay, so there's a bus going up a 6% grade here, or not 6%, a grade that's 6 degrees to the horizontal, constant speed. We know the mass of the bus. What's the rate of increase of GPE of the bus? Okay, it's kind of an interesting question. The rate of increase means the amount that the gravitational potential energy is changing every second. So let's consider 1 second to be our time scale here. In 1 second, the vertical height gain, okay, because it travels 6.2 meters diagonally up at 6 degrees in 1 second, we can use simple trigonometry to find out that its vertical height gain in 1 second is 0.648 meters. Okay? If that's the case, the change in potential energy per unit time is mg delta h over delta t, and I got 54 kilowatts for that one. Okay? For part B, the total output power of the engine is 70 kilowatts and the efficiency is 35. Very simple calculation to calculate the input power to the engine. We just rearranged this very simple equation to solve for Pn, and I got 200 kilowatts for the input power to the engine.